Let us now study important applications of Gauss law. The first application, that is electric field due to an infinitely long charged wire. So there are three applications totally. This is the first one. It's an important 5-mark question. So let's go to the concept here. So first we'll take a long wire, okay, a very long wire like this way. This wire has been positively charged. So let's give it some positive charges, and then it has a linear charge density lambda. Okay, the linear charge density is given by lambda. Then we'll consider a point P here. So point P, it is at a distance of r from the wire. So this thing is a wire and this is a point here. Okay. Now our aim is to find what is electric field at this point. Okay. Now let's go to the picture here. So this same picture I'll take. Okay. I'll draw it here like this. This is the same wire only. It's not a different thing. It's the same one. Okay. Again, it has positive charges. Then let us now take two areas here, or two charge elements. Okay. Let's take two charge elements. So this portion is a charge element here. Let's name this charge element as A. Okay, that means it's an area, it's a part. Then here also take another charge element. Let's name this thing as B. Now the point P is here. This is the point P. Now you know that the electric field lines, due to positive charge, they always go outward. So this electric field line will be, or the electric field will go like this way for the first one. Then for down at point B, the electric field line will go up here. This is the point B. I'll write it more clearly. Okay. Now at the same way on the left side also we can see that here the electric field due to the top charge element, this charged portion. Then at point B also the electric field will be like this way. Okay, these two meet here. Now if you notice that the distance we mentioned between here, between the wire and the point P was R. Now if you see it's in all the sides. Okay, this is a wire, means around the wire there will be an electric field. So it will be in all directions. It will form like a circle. Okay, so this portion is like a circle. It surrounds the wire. So the electric field around the wire is like a circle here in this thing. Okay, due to the two elements here. Now if you notice that if we add many circles, we'll get a cylinder. Okay, you can imagine like coins. If we keep on stacking coins, then finally we'll get a cylinder. Let's see that now. Now I kept a 2 rupee coin here. Let me keep some more coins here. This is another coin. Like this way, I'll keep many coins like this on top. Okay. Now I kept a lot of coins there. If you see that each coin was like a circle, but if you see it together, they are like a cylinder. So in the same way, the electrical field will be like a cylindrical cylinder. Okay, so we'll choose a Gaussian surface which is like a cylinder. So let me draw the wire again. Yeah. Okay. Now let us see the charges here. It has been positively charged. So positive charges. Then we have the Gaussian surface. Okay. I said the Gaussian surface is like a cylinder. So let us draw that thing here. If you see the Gaussian surface like a cylinder, so I'll draw a top portion here. It's like a circle. Then on the bottom also like a circle. I'll extend this slightly. so it's more clear to see the concepts here. Remember, this wire is infinitely long. That means very, very long wire. Okay. And then the bottom surface, it will be like this way. Now we connect these two, because we saw it's like a cylinder, formed like cylinder. Okay, it's a cylinder. Then, so this green thing, it's a Gaussian surface. This is Gaussian surface. It is cylindrical. Okay. Then let us see how the electric field will be. Okay. So let's see the electric field and the normal. So at this point, at the top, okay, let me take the top surface. At the top, I'll take a portion here. Okay, let's take this portion here. At this portion, the electric field will be like this way. The electric field is like this. E is a electric field, it's a vector. Then at this point, okay, you see the normal will be like this way. I'll draw using another color. For example, let me draw it using this color. So this is normal here. That is n cap. So normal and electric field are perpendicular. Okay, let me choose another color itself for normal next time. Then at this portion on the curved surface, so we'll take small element here. Okay, small element dA. The electric field will always be outward. Okay, you can see that. For positive charge, electric field comes outward like this way. So arrow mark is like this way. So this is the electric field. It will be outwards. Let's see the normal here. In this case also, the normal, if you see, I am using this color here, orange color. This is a normal n cap. You see that the electric field and normal are both parallel. Okay, let us take another portion down here. In this portion, let's see the electric field. The electric field will be outwards again because positive charge, you know. So electric field will be outwards. But let's see the normal here. How the normal is? Normal to the surface. Okay, so normal will be like this way, n cap. Okay, so the electric field and normal are perpendicular here. Now let us see how to calculate the total flux here. Now the formula for electric flux we know, that is phi E. That means electric flux is equal to closed integral, because we have closed surfaces, into electric field dot dA. So electric field into the area vector. Now you will notice that this thing, okay, the closed surface. So what is the closed surface? What are the parts of the closed surface? Let's see that now. Again, we'll go back to the picture. If you notice now, there are three surfaces. One is this curved surface. The cylinder has a curved surface. This is curved surface here. Then we have top surface and a bottom surface. So the three surfaces, and they have three different fluxes here. Let's calculate that. So for the first one, we'll have the closed surface, the curved surface here. We'll take a curved surface. Okay. The cylinder has a curved surface now. So I'll take the curved surface and E vector dot dA plus the second one, that is so you will take the top surface here. The cylinder, remember the cylinder has a top surface. The top surface will take that. So in this case also we have E vector dot dA vector, the second flux. Then third one, remember the bottom surface we had now, that also we write down. So bottom surface, again here also E vector dot dA vector. Now we know the expansion of this one, A vector dot B vector, AB cos theta. So E vector dot dA vector will be E dA cos theta. Let's write that now. So let me write this down. So first one, integral of for the curved surface, okay, that will be E dA cos, okay, cos of theta. Let's see what will be the angle for the curved surface and the electric field. Okay, let's go back to the picture now. Now you notice that this is electric field and this is a normal. The angle between the electric field and normal will be 0. Okay, but for top surface the angle between the electric field and normal will be 90 degrees, and for bottom surface it is also 90 degrees. Okay, so let me take the first one. The angle between the electric field and the normal, that is 0 degrees. So cos 0 will write. So EDA cos 0 plus the second one EDA cos of the angle you must see. This for top surface. Let us see for top surface what will be the angle. Yes, for top surface the angle between the normal and the electric field. So normal was here, the electric field was 90 degrees. For bottom surface also at 90 degrees. Okay, so that will be cos 90. So that will be EDA cos 90 plus for bottom surface also closed integral for the bottom surface, or so the integral of the bottom surface will be EDA again cos 90. So what will happen? Cos 90 we know that is 0. So for this term will fully become 0, and this term also will become 0 here. So but let's take this cos 0, first one. What is the value of cos 0? Cos 0 value is 1. So we'll get here closed integral of EDA, because cos 0 is 1. Let me write that down here. So we'll get here integral of EDA. Okay, so this will give us the electric flux here. Okay, so this is phi E is equal to EDA. Now we'll see more this in detail. So the electric flux phi E will be equal to, I'll write it one more time, that is for the curved surface. Okay, curved surface only we have this, that is E dot dA. So not even dot, just EDA. This is not even vectors. Okay, EDA, and on this side you will have here Q enclosed, the charge enclosed by the epsilon naught. This is the Gauss law. Okay, this one we'll take here. Next, if you notice that the electric field, okay, it is constant everywhere or on the surface. So electric field is a constant, we can take it out. So we can take electric field out because electric field is constant, and integral of dA, that's equal to Q enclosed by epsilon naught. Okay, so what will be the charge enclosed? Now if you notice that we have this thing called as the linear charge density lambda. Lambda is equal to Q by L, charge by length. Now from this what will be Q equal to? Sorry, this is lambda, so Q by L. So if you cross multiply this way and rearrange, Q is equal to lambda L. Okay, so I'll substitute here in this thing. So instead of Q we have here lambda L by epsilon naught. Okay, now this dA, what does this dA means? Integral of dA, that means sum of all the small elements. Okay, let's go back to the picture again. So in this picture we have taken, this was a small area. Now in this way we'll have many small areas like this, dA, like this. You have to add all the small elements, so we have integral. So if you add or see the area of this curved surface, they say according to maths it is 2 pi RL. Okay, so let's write that and see. So instead of integral of dA we have E into 2 pi R L is equal to lambda into L by epsilon naught. Let's see what will cancel. L and L will cancel, the length cancels. Then we can bring this 2 pi R down. So what we have here, that is electric field is equal to 2 pi R, no sorry, 2 pi R will come down only. So electric field will be equal to lambda, let me write it more clearly. Electric field is equal to lambda by this 2 pi R, no 2 pi R comes down, 2 pi R into epsilon naught. So this is the formula for the electric field due to infinitely charged or infinitely long charged wire. So this is the formula that we need. E is equal to lambda by 2 pi R epsilon naught. Lambda, E means electric field, lambda means the linear charge density, R is the radius or the distance of the point, not even radius. Epsilon value we know. So if you substitute these things, we'll get the electric field. So this is generally. But if you take vectors, okay, in vector form, we have here E is equal to lambda by 2 pi r epsilon naught, and let's write vector here. Because the distance is a vector, we write as r cap. This is a vector form. Okay, it's enough that we write up to here. Okay, you can also write this also, but this is usually more useful. So E is equal to lambda by 2 pi r into epsilon naught. See the formula one more time. E is lambda by 2 pi r epsilon naught. In this formula, you can see the electric field is inversely proportional to the distance. Okay, as you go far away, electric field will decrease. It's not 1 by r square. Okay, next is one more thing we must know. See the lambda. Okay, this is another thing to note. If lambda, that is linear charge density, is greater than 0, then the electric field E will point outwards. Okay, then if the lambda, that is linear charge density, is less than 0, okay, then the electric field will point inwards. Okay, outwards, it means positive charge, then inwards will be for a negative charge.